This is all basic stuff. I'm just setting up some things with these slides. Research drives this. That's what Peter Lemedico and his colleagues are all doing over on our research side. Another big piece of this, increasingly these days, is advocacy. So, how many people in this room are grassroots advocates for JDRF? I was with one person earlier who I knew was going to sign up. A few hands, come on, I only saw a couple hands go up. I need to see, everybody's hands should go up. This is like the single biggest thing you can do, right? People say, what can I do? This is one of the simplest, most powerful things that you can do. Becoming a grassroots advocate for JDRF is simple as you go to our JDRF.org website and you click on advocacy and become an advocacy member. It's a simple thing. Once you've registered, they will just send to your phone or to your computer an alert that says, we need your voice to be heard by Congress. We need your senator to hear from you. We need your congressman to hear from you. Or we need the FDA to hear from you, right? This is JDRF harnessing the power of all of our voices all around the country and going in and making our voice heard so that we get the regulatory environment that we need to get artificial pancreas technologies to us or encapsulation technologies to us, or that we get renewal of special diabetes program funding through Congress so the NIH has money to spend. So I'll tell you a really interesting story. Last week, I was at University of Utah speaking, and it was all researchers. And I said, so how many of you are JDRF grant recipients who are under contract to JDRF to do research? And a number of them raised their hands. And then I said, and how many of you get NIH funding? Every single hand went up. And I said, that funding is there because JDRF advocates all around the country lobby Congress to make sure that money is passed on an annual basis. What would your world look like if that evaporated? And at the end of that, I think they all went and became grassroots advocates for JDRF, right? Because that's $150 million every year. That matches the $100+ million that JDRF spends every year to fund research in the world of type 1 diabetes. It's incredibly important, and so I really have taken a minute to do a commercial for becoming a grassroots advocate. But I would encourage all of you, is the chapter's grassroots advocacy person in the room by any chance? There she is. Raise your hand. Talk to her after this talk. It's an incredibly important thing. The great news is, just this week, we saw a renewal of the special diabetes program for 1 year, another $150 million. So imagine how tough the fiscal environment is in DC right now, and yet in the middle of all this, we've been able to renew. At the middle of the fiscal cliff, a year ago last December, we got the renewal through. And it's because all of us made sure our voices were being heard in DC. So really, it's an important thing. Please do that. Anyway, all of this is to drive research, advocacy, this pipeline, driving everything to delivery in patients. I want to move forward to concrete stuff. So now I'm going to really start to drill down and give you super concrete information about some things that illustrate what I was just talking about. And hopefully, I'll drive home with a vengeance, lots of this. Any questions? It's a really good group, very quiet. All right, so what is an artificial pancreas? I just always do this to make sure that we're all on the same page. This is a market where I would expect most of you have heard about artificial pancreas technology. So artificial pancreas technology is three things. So one simple thing is from a company that's based here, which is the Omnipod insulin pump. I just happen to wear this pump, but it could be any kind of insulin pump. So this is my particular version of the pump, so I just happen to have it in my pocket. But it's an insulin pump. So this is a technology we're all pretty familiar with. It's a fairly mature technology. We want to see it become more mature. We want to see it be able to do some more things. But fundamentally, insulin pump, and then a continuous glucose sensor, right? And I, curiously enough, am wearing one of those, and I ate dinner, so we're going to find out how well I'm doing. 163 in the level, that's not too bad. So I just pushed a button instead of pricked my finger, right? So this is the equivalent of pricking my finger several hundred times a day, only I don't have to. Right? Instead of bleeding all the time, I'm able to push a button. And if I go too high, this will alarm at me. And if I go too low, this will alarm at me. So this is like a little coach in my pocket. This is a huge advance in the management of type 1 diabetes. This just happens to be Dexcom, which is a California company, another partner of ours. How many people in this room use CGM? Wow, really good number. That's great to see, right? So this is really important technology. So artificial pancreas then is combining the two things. We want to combine the pump and the sensor so that the two can talk to each other, right? And the piece that was missing historically was the communication piece, was the computer program that would take the real-time data feed from the sensor and give instructions to the pump. And so JDRF back in 2005 began to decide, the environment has we've reached this world now where we're using more and more wireless devices, and we think that for the first time we might actually be able to start trying to automate this system. So JDEF really looked at it and asked the question, do we need an artificial pancreas, right? Is this a place where JDEF should spend some money? And JDEF had just finished funding a study on continuous glucose sensing, and from it we were able to see that even people who wear continuous glucose monitors, who tend to be better controlled, spend 41% of their day too high and too low, out of bounds, right? And of that, actually some pretty good sized chunks way too high and way too low, scary high. So even people who are tightly controlled have bad numbers. Another way, there's the T1D exchange, which is something that operates here out of Boston. 26,000 type 1s all across the country, all of whom are going through clinical centers, and those clinical centers are some of the best sites around the country. So nominally, these are people who are really well informed and hopefully are doing a pretty good job of taking care of themselves. Fewer than 30% of them meet the target A1C of 6.8. The average A1C is over 8. So fundamentally, that's really a lousy number. What JDEF fundamentally decided was, yes, probably we should be looking at artificial pancreas technologies because this has the potential to change all our lives. And I've got a question over there.
Yes, just for this study, what were your definitions of out of bounds for too high and too low?
So it was basically above 140 and below 80. Right? Or actually it was below 70. I'd have to go back and look. It's going back a ways. But it's what the clinical definition of normal blood sugar range is. But I could actually break that out and show you. I mean, the data is there. You can see it was published in the New England Journal of Medicine. You know, how high, over 200 and below 50 kinds of numbers. You can see all that. That's there. And people spend time every day in those, not every single person does, but lots of people spend time in those places every day. Right? So most type 1s spend time over 200 almost every day. So the idea was to see if we could change this, right? Change the amount of time spent out of bounds. So this is me in 2008. And I've got a smile on my face, which is always a good thing. JDRF launched this work in 2006. We did a modest investment of dollars with a consortium of researchers, 16 different institutions around the globe, and it really is global, to say, okay, can we come up with software that can close this loop and allow this automation to begin? And the great news is, and I'm not going to go into all the detail on this, is that very rapidly, we were even able to skip animal testing because we came up with an in silico, a computer-based model of humans, and run tests of the algorithms in the computer to show that it worked, and the FDA accepted the data. And just that alone, JDRF drove that with some amazing researcher, Boris Kovachev at the University of Virginia. That single thing all by itself shaved probably 7 to 10 years off the development timeline of artificial pancreas technology. It's a huge thing that we were able to make happen. So we were able to very rapidly jump into, remember I was talking about that translational pipeline space, we were able to jump from something that was just an idea in laboratories into a human being in about 2 years, which is a pretty extraordinary feat all by itself. And my endocrinologist happens to be the lead endocrinologist on this project at University of Virginia, and since I'm her patient, she said, I think you should do this trial. And because I didn't know what it meant to be a guinea pig, I said, sure. And here I am being a guinea pig. So you can see I've got lots of wires attached to me. I've got this fanny pack. I have this flannel shirt on because it's January and they've got an IV in every arm. And I'm just realizing Alan Berkowitz is in the room. I hadn't seen you, Alan. Sorry, another colleague is in. There's lots of people in this room that I don't.
So how does the CGM work? Oh, you don't have to prick your finger. So
right, so how does the CGM work and how accurate is it? So the good news is the technology is getting better and better and better, and it's more and more accurate. And it's basically a fiber. It's about the size of a human hair that's just inserted underneath the surface of my skin. That's right now it's on the back of this arm. And it reads out to a little device that beams out, that has a battery and an antenna, and it pushes out the signal to a receiver. And so it's just it's a fiber inserted in the body that's able to chemically react to glucose in the interstitial fluid. So that's how it measures it. And accuracy is getting better and better and better. It's remarkably accurate, frankly. I can go into details on this that will be lost to most people, but they're becoming more accurate than finger sticks in many ways. It's very interesting to kind of see this technology jumping forward. The good news is JDRF is even driving next-gen sensors that are way beyond the ones that we currently are using. So the real question is, are the ones we have right now good enough to power the artificial pancreas? And what you're going to see here in a second is pretty much yes, but we're going to make them even better so that we can get even better artificial pancreas systems.
How often do you check otherwise? Do you check otherwise?
So So officially, the FDA says I'm supposed to check my blood every time I'm going to make a therapeutic decision about giving myself insulin. You definitely have to calibrate twice a day. You have to do a finger stick. And beyond that, talk to me later when we're done. So, now I'm going to blush red. So, I do still test occasionally, but sensors are remarkably accurate and they do some really good things for us. So, but this was the very first time, right? So this was in a hospital. This was a phase 1 clinical trial, so it was safety, safety, safety. I had to wear 2 pumps, 2 sensors, right? 2, because of when it fails, we have redundancy. Trials, when you go from mice into human beings, cost you lots of money. So you need to have backup so you can keep going if something breaks and not have to restart, which would cost us a lot of cash. The burn rate on trials is very, very high. So this is me in the hospital with lots of wires. And again, as I had an IV in each arm, and they can't use the traditional drug that prevents the IVs from clotting because it gets in the way of some of the measurements they're trying to do. So they had to keep me as warm as possible, so I was kind of roasting the whole time, so that my blood would continue to flow. And every 5 minutes they were coming and pulling these little bullets of blood out of my arms. It was kind of fun. And then they have got me, all of these devices were hardwired into 2 laptop computers that were sitting right here, right? So this is me with a smile on my face, though, because I'm incredibly excited because I sat there and ate every meal and didn't have to do anything, right? So how many type 1s would love to eat meals and not have to do anything? So I'm texting and emailing people all over the country going, oh my gosh, this works and it's great and it's fantastic. And oh, by the way, I've got all this stuff attached to my body and I can't get out of the bed and going to the bathroom involves me and 3 other people because the whole cart has to come with me down the hall, right? So it's kind of crazy, but I was having a great time. And how did the system do to start? Right? So this was old technology. This stuff is all dinosaur technology now. There's actually an artificial pancreas museum, and that stuff that I was wearing is in the museum. And it's only 2008. So how fast are we moving? As fast as we can move. So between 9:30 and 8 o'clock at night, kept me between 80 and 110, right? Just right out of the bat. Used 48% less insulin in the overnight. That's extraordinary. Shut off my basal for periods of time, actually for 4 hours. Because it had me stable. And once I was stable, it didn't need to tweak me much. That was kind of interesting. Each time you go in and you run the show by yourself, and then you replicate it with the system running it. You eat the exact same food, weighed out to the very last gram. You have to eat it at the exact same time and eat it the exact same number of minutes each time. So you're trying to replicate so you can have a control and then a period where it runs you. So when I ran the show in 24 hours, I went low 6 times. Is that typical for me? Some days. Right? It wasn't this particular day. Low was 69 for an FDA protocol. And I had 1 high and it had 1 high. But remember I was talking about that time out of range? I'm a pretty tightly controlled type 1. I don't always share this, but until my last A1C was 5.9. So I worked pretty hard at keeping where I am. And in 24 hours, I spent more than 4 hours out of bounds. When the system took over and ran me, the very first time ever that it was tested in people, it shrunk it to under 40 minutes. Right? That's powerful. And oh, by the way, I didn't have to do much to manage my diabetes. So you can imagine we were pretty excited, and we moved forward. 2 more years. And now you'll notice that I still have the fanny pack on, but there's a lot less wires, and I can actually move around. But oh yeah, now that means they're putting me on an exercise bike and taking me to 100% of capacity for 30 minutes at a time. Aaron Kowalski, if you've ever met Aaron, he made me swear I would never use this picture in public, so I've officially broken my promise to Aaron. But they also measured your O2 uptake and your CO2 release. They measure every single part of your body and after the exercise. So this was me doing the exercise. This particular version of the trial was trying to force you to go low due to exercise to see how the controller could do. And I can tell you all the details. It did amazingly well, right? But think about this. 2005, this is a concept. 2006, we do the very first funding. 2008, you saw me in the hospital bed. By 2010, I'm somewhat ambulatory. I can get up and move around somewhat. And I was looping into a wireless network on the hospital floor, right? When we launched this trial, smartphones didn't exist, right? The iPhone didn't come out until 2008, and later in 2008. So the great news is, by 2012, here it all is, and I actually have this on my another pocket. So there's the artificial pancreas, right? So that's just a smartphone with an app on it, and the app is the artificial pancreas. It's just a Samsung Android phone, And just for all those of you who worry, it can run on an iPhone, it can run on a Windows phone, it can run on a BlackBerry, any phone that can run the app and have Bluetooth capabilities to connect with various pieces of the technology can run this, right? And I'll be glad to show this to people later. But literally, they handed me this phone and said, hey, go, go live your life. So think about what I was talking about, driving things through the pipeline. First, we're doing the early trials that are all safety trials in the hospital. You can't leave the bed, right? Then you can just move around on the floor of the hospital. Now they're handing this to me and saying, go out and live your life for 3 days. Go do whatever you want to do. So, being who I am, I did. First thing I did was went and get a Five Guys cheeseburger and some French fries, right? That's a Virginia-based company from an area where I grew up in Virginia. And my endocrinologist, this is her right there, Stacy Anderson, was with me, and she looked at me and she said, you're really going to get a cheeseburger? And I'm like, yes. I'm going to test the system. So I ate that cheeseburger. I told them that, and I have to be honest, I did not eat all of the Five Guys fries because I just couldn't do that to my blood sugars. Whoops. And I just did something that made it go away. Maybe I did that. So, give me just a second. Was that a glitch? Was in slideshow, yes. There we go. I told it that meal, Five Guys cheeseburger and fries, only needed 1.9 units of insulin. So how many type 1s would say that was enough insulin for that meal? I had purposely underpitched it. And started to go up. The system started to give me extra insulin, and I peaked about 190. Plateaued, and I came back down. The system was working to keep me under 200, which it did very nicely. By bedtime, I was back to 100, right? So I'm talking to my doctor, and I'm like, Stacy, this is great. I'm so happy to be back to 100. But it's been giving me extra insulin here, and it's 11:15 at night. And usually, if you give me extra insulin at 11:15 at night, I'm going to go low in the middle of the night. And she's a pro, and she's like, let's just wait and see what happens. If we wake up in the middle of the night, we wake up in the middle of the night. We'll see. The next thing I know, 7:30 in the morning, and I was still at 100. Right? And so how many people would love to have perfect control every night? The second night, ate a really fancy meal, had a hot veg sundae. Went over about 160, 165. Bedtime was 100. Woke up the next morning as 100. So that's how powerful this technology starts to become.
What type of insulin are you
Humalog.
using? Humalog.
Yep.
I even find that's not quick enough.
Yep.
And even some of the competitors are not quick enough. I don't know how you did that.
So the amazing thing is, technology. So my colleague Aaron Kowalski will say, better is the enemy of good enough. What we have right now, when you allow technology to take over and run everything that's going into your body, and it can really track, and these very powerful algorithms are making decisions, and I could explain how it all works to you, but I'm not going to. We'll be here forever for that. But you can start to see some pretty amazing control. Is it perfect? No. Is it amazingly good? Yes. Can it get better? Absolutely. So that's where then JDRF is looking at, are there other forms of insulin that we can get or use, or other ways of delivering insulin that can get it on board a lot faster to deal with that issue, right? Can we use sensors that are the size of Tic Tacs that use fiber optic based technology as opposed to the kind that are chemically reactive that I use right now? Absolutely yes, and not only that, but I've tested those. Those are a partnership with Becton Dickinson. JDRF is funding this as next generation sensing technology. They're the size of a Tic Tac. They use fiber optics, so glass, with a material baked into them that reacts to the presence of glucose, and put it on 10 minutes after it's on. It's calibrated, and it lasts for 30 days and is incredibly accurate, right? So you can see, step by step by step, JDRF is driving. So remember we were talking about less until none, right? Less burdensome, less complicated. So here's a technology that we put it on, and I was able to go eat a Five Guys burger and fries and not spend the next 4 hours sweating every detail of what's going on in my body. Right? I literally got to just hang out with the researchers and talk to them, and then look at it at 11 o'clock and go, wow, I'm actually back where I'm supposed to be, and I didn't do a thing. The system did it for me. Right? This is powerful technology that improves the quality of our life, and I will tell you, nobody's yet worn this for 90 days. But people have worn it up to a week in various different trials, and there's more than one kind of artificial pancreas system. We're working on multiple generations, but All of them basically, if you look at the data and aggregate it and say, if a person had worn this for 90 days, and we saw this similar performance across the 90 days, A1Cs land somewhere between 6 and 6.2, right? Remember I was talking about the fact that fewer than 30% of adult type 1s are able to reach their target of 6.8, let alone that level? And here's a technology that all by itself would put everybody pretty much where we want them to be. Is it perfect? No, it's just technology. Is it a giant step forward that improves quality of life, reduces danger, reduces complexity? Yes, it has its own complexities that come with it. This is only one step of many, and I'm going to talk about some other things.